Hello and welcome to this GigaOm webinar. We're here to talk about observability and the return on investment crisis around observability. So there's a few things that you might be thinking out there. You might be thinking, well, what the heck's observability? What the heck's ROI? And we all know what a crisis is right now. So let's cover what broke in observability and how do we fix it. And here to help me to talk about that, I've got Ben Sigelman from Lightstep, founder and CEO. So you've got all the right titles there, Ben. Why don't you introduce yourself and say what you want people to get out of this webinar?
Sure. Thanks for having me, John. I'm pleased to be here. I'm at Lightstep now, of course. Previously, I spent about 9 years working at Google on their distributed tracing and metrics systems internally, which are similar to observability in many ways. The reason why I wanted to choose this particular topic is I think observability has gotten a lot of airplay in the last year or two, especially in marketing materials, but I don't think it's particularly well defined for people. And then I see the market making a lot of moves into observability that, as per the title of this, create ROI problems, both on the return side and the investment side. And I thought it'd be good to dig into that a little bit as well.
Okay, and part of the challenge, as we're going to cover, is the very nature of the kind of systems that we're talking about today. And your term, Ben, is deep systems. So we're going to go into what they are. Why does observability become so important? And then the whole notion of telemetry, the different types of telemetry you might want to use, from logs to metrics to all that kind of stuff, and how that can fit together to resolve some of these issues. So what does a unified observability strategy sound? It all sounds a lot like jargon at the moment, and I know that it's not. I'm really looking forward to putting some meat onto this bone, and then we will make it more concrete throughout, and give some people some screenshots to dwell into that. So to kick things off, then we want to see what the challenge is. We want to see first, maybe, what do we mean by deep systems? So I'm going to hand the baton over to you, Ben, and maybe you can start describing what we mean by deep systems here.
Yeah, sure. I mean, I think to start this, it's helpful to step away from technology for a moment, or at least information technology, and to think about the different ways that things scale in the first place. I like to think of things either scaling wide or scaling deep in a very general sense. So an example of something scaling wide would be a puddle. If you have a puddle, you have just a bunch of water, obviously, and as you add more and more water, you just get a bigger and bigger puddle. There are certainly many things in life and in the world that scale in that way, and the essence of things that scale wide is that you just get more of something. That's really all you're getting when you scale it, and those things are typically easier to scale from a technology standpoint, which we can talk about later. When you're talking about things scaling deep, it's very different. Where so on this these pictures in the bottom row here, if you have some kind of village and it's suitable for maybe 100 people or something like that, as you scale that out to support tens of millions of people, it's not that you just have a lot more houses in your village. It's a totally different thing. And things that scale deep, the deep version, it's not just more of the small ones. It's different. It's fundamentally different. And what I've observed by talking with folks in the market and through my own experiences is that when systems grow large enough in terms of the number of different components in the system, they don't just scale wide, they scale deep. Because they scale deep, the tools and technologies you would use for smaller systems, you can't just continue to use them in the deep system. It breaks the assumptions that you made in the small system, just like the sort of electrical grid you need in a city in no way resembles the electrical grid you need in a village. It's similar. The technology and tools you need for deep systems is very different than for smaller systems.
And it's interesting. I mean, we're using the term scale here, which I mean, obviously, it's all over the slide. But you mentioned scale out there, and back 20 years ago, we were talking about scale out as being a hardware feature, if you like. And so you could scale up in terms of the number of things you had in parallel, or you could scale out in terms of how you balance the load across infrastructure hardware. Whereas here we're talking about scaling from a software perspective, and how the complexity increases.
Yeah, and I think the thing that's so fascinating about it is that the I think as technologists, we tend to think about the technology. The real driver for the depth of these systems ends up being engineering management, I think, more than it does any particular software or hardware problem. And I completely agree that there's always been a need to scale, within any domain since we started working with computers. What's different this time is that if you have hundreds of engineers working on a single application, which is a relatively modern phenomenon that was very rare in the 80s and 90s by comparison, you really can't get more than 10 or 12 developers to work on a single piece of deployed software successfully, which is really what's driven the transition to adopt microservices and serverless. It's the idea that you need to have relatively small teams working on independently deployed pieces of software. And those independent deployments are really what create a lot of the hazards in deep systems, which we'll talk about later in this deck as well. But the thing that's scaling is not just the software, it's the organization. The two are actually scaling together.
And well, here's a chart. Is this a software chart or an organizational chart, or does it not matter?
Well, that's a great question. I think, there's Conway's law, right, which is that, I can't remember the exact phrasing, but it's this idea that in any organization, the organization and the system end up being isomorphic in some way. So you end up with microservices, you often ship your org chart is sort of the joke, but I think it's actually pretty accurate. And what we have here on the top is, these are just completely superficial examples I made up in slides. We'll show some real examples, I think, in the following slide. But on the top is an example of, there are definitely software systems that do scale wide. I think an example would be like a Memcache deployment or a MapReduce, where they're quote unquote embarrassingly parallel. These things do exist, but when it comes to applications built on microservices, it turns out that it's much more common, if not downright ubiquitous, that the system ends up scaling in a deep way, where you have many layers of independently controlled services from the top of the stack all the way down to the bottom.
And it's one of those things that I think we talked about this on previous calls, where back in the day, software, the notion of software modularity was always a good one. And so, right sizing your software components or your software modules or whatever unit of delivery you're talking about, and then minimizing the dependencies between them. All of these things are really good, but then distributed systems kind of broke the model. It was really hard because of networking to manage the interfaces. But now we've got a situation with containers and with much higher speed internetworking and cloud computing, where it's possible to build these very complex systems that scale both wide and deep.
Exactly. Yeah.
That was a bit of a long. Don't you think, Ben? I could have added at the end. So,
yes.
So and you said that there's some real systems, and so here's some examples. They look as much like hardware to software to my undiscerning eye.
Yeah, I mean, I've intentionally blurred these out because these are all Lightstep customers, which is only relevant because these are systems that I can access the data very easily. But you have 4 different pictures here. On the top left, I think there is a system where each one of these circles is not just an instance of a service, but it's like a different type of service. Like a service might be something that handles credit card payments, or a shopping cart service. Even if you have 100 copies of that service, there's only one circle in these diagrams, and it just shows the architecture of these systems. So when you have relatively small number of services, like 15 or 20 services, you already see in the top left that they're arranged such that there are more than 6 layers of depth between the top and the bottom of the stack. If we go to the top right image here, this is about 50 services, and I have to count, but I believe it's about 9 or 10 levels of depth between the front end at the top and the storage systems at the bottom. As we continue here, you're seeing systems that, I think the bottom left picture here is an architecture with about 100, 200 services, and then the bottom right was thousands. And I literally can't capture a screenshot of the whole thing because it's too big. But this is absolutely typical. I didn't handpick these in any particular way. I just tried to get systems at different scales, and I just wanted to illustrate how these things actually lay out. And when we started the company, I actually wasn't sure what the architectures would look like in general, but absolutely, without exception, when you have dozens or hundreds or thousands of microservices, in any case, you end up with these deeply nested systems where each one of these layers, because of the beauty of microservices in continuous deployment for each team, each one of these layers can be changed and is changed frequently and independently, which is what causes so much of the pain, which we'll talk about later.
And I'm going to flip onto the next slide, whether you like it or not, because it's kind of talking about the stuff you're talking about. But I've also got a question around this, which is the notion of the top and the bottom. And this is a complete duffer's question, so bear with me. But my understanding of microservices is that they're kind of distributed, and they've all got a level of equality. If that makes sense, each one's talking to each one, and there isn't a God object as such. So it is the nature of it. So is it a bit kind of George Orwell's Animal Farm, where all services are equal, but some are more equal than others? Some take that kind of authoritarian position. How does it work?
That's a great question. I think that typically there are probably other patterns that are more eccentric, but most of the time people arrange microservices such that especially if you're handling transactions, which most user-facing applications are handling transactions, such that the transaction first hits some kind of top-level service that actually processes the transaction. It then routes that into some kind of descendant service, which then routes it and routes it and routes it until you end up at a storage system or something like that, and then it comes back up the stack. Sometimes you have people building things around message queues like Kafka, but even in those situations, you still have some services the first touch for an end user's request, and it will go through Kafka or not, but ends up traversing the services in some kind of standard order. So what I mean by top and bottom here is just the first service to handle the transaction would be at the top of the stack, and then it goes down from there. So it's not so much that they control each other. I think from a control plane standpoint, they really are peers more than anything else. But from a transaction processing standpoint, there's a natural hierarchy in terms of user touches and stuff like that.
So it's a kind of sequence diagram question as much as anything. Is what touches the service first, and then what's it hand off to? Cool. We're going to have, I think I get that, and let's see if the audience gets that, because we're going to have a poll. I'll move to the poll question, if we may, and as we're doing that, I'm going to read the question for the watchers and listeners out there. So the question is, how deep is the software application that you're working on? That is, how many separately deployable layers are there between the clients at the top of the stack and the infrastructure at the bottom? And so this should actually be a select one. It says that, so that's fine. So if the attendees out there could say whether or not their software application is relatively shallow, it's got less than 3 levels, or if it's got 3 to 5 or 6 to 10 or even 11 plus, or quite simply, you don't know a way to measure this. And if I turn back to you, Ben, while people are answering this, what level of depth is normal, or does that question even make sense as a question? There is no such thing as normal in software.
I mean, most software, if you're really going to be general about it, is a spreadsheet. Like Excel is a type of software, so in those cases, there's no services, right? And then you get the software that's like a 3-tier app where you have a web application that's on top of some kind of simple SQL database. That would be a quote unquote less than 3 type of software application. Once you start dealing with software applications that businesses are betting their future on the other hand, then you start requiring hundreds of developers, and once you get into that world, the depth gets much larger. And so I would argue that the software applications that are defining the future of our economy end up often being quite deep indeed, and the software applications we use to balance our budget in some kind of departmental situation is probably just a spreadsheet, you know. So software is a very broad term, right? But for business applications that are really high value, high leverage, I think you often end up with 6 to 10 plus levels of depth in these architectures.
Okay, and that seems to be how it's coming out. And as a matter of interest, what level of expectation do you have? I mean, is this still early days for the market, for industry adopting more cloud native applications? So are you expecting to see much more complexity emerge, or are we already in a very complex situation right now?
I think what we've seen, it's been interesting in the past couple of, even in the past year, I think we've gone from having folks tinkering with Kubernetes in kind of a laboratory environment to actually running it in production. At most large enterprises have some piece of their, you know, flagship software running in a cloud native environment, but they also have some other pieces of it that are not. So I think we're really in the thick of a transition, which I expect to take many years. There are some organizations that have been very forward on this and are most of the way there, but I would say that's probably, you know, less than 20% of them, something like that.
Cool. Okay, so that's all very interesting, and what's also interesting, therefore, is what is then going to cause problems within that. So let's start delving into what kinds of challenges this causes. So first, the notion of this number of services against developers per service, that the number of developers per service drops right down as the number of services increases. Is that a parallelism thing, or is that just a kind of is that the way it should be, or is that the way it shouldn't be? What's going on
It's
here?
just the way, I think this is just the way it is, unfortunately. This goes back to the engineering management thing, where if you want to have more than, let's say, 15 or 20 developers working on a single service, whether that service is a monolith or not, I don't care, but it's just really difficult to do. I think CI/CD starts to break down when you have too many people committing code. And this transition, in my mind, is totally inevitable, and that the companies that choose not to make this transition and choose to stick with a small number of services despite a large number of developers will develop software so slowly that they will ultimately be eclipsed by more agile competitors. So this is really it's being driven by a business need to be agile and to innovate quickly, and it's good to have fewer developers per service, but as you have more services, you end up with a deep system, and that again, I think, breaks your tool chain in a fairly fundamental way, especially from an observability standpoint.
So, I mean, this is the kind of a good cultural change to make. It reminds me of well, it reminds me of the very old adage that real programmers can write Fortran in any language, but it also reminds me of various experiences throughout my career of helping organizations with you know, 3-tier architecture or multi-tier or whatever it is, where each time on more than one occasion they just built a single stack monolithic application using whatever the latest technology was. So in one case it was using it was JBoss, but building a complete, you know, non-maintainable single chunk of software using JBoss. So what we're seeing here, as you're saying, is that organizations are moving into a more deep systems culture, which is great, but then that starts kicking off certain problems, which we'll see, and we'll start, if we may, bring in terms like observability and its role. So maybe start. I mean, what does observability even mean? Should it be obvious? You tell me.
Observability as a term dates back to the 60s, and it really has to do with your ability to understand what's happening in a system, given just the data that's coming out of the system. So the idea is that you basically, I mean, in software terms, to make that less abstract, it just means that you don't need to redeploy your software to debug it. The software is describing itself well enough that you can understand it just based on the tooling that you have. That's what observability actually means. What it's come to mean in the industry is much more complicated. I think with this particular imagery, I think this is actually more general than just observability. It's just one of my favorite definitions of stress, which unfortunately in these
You have many?
COVID. Well, this one's really short, but in these COVID times, I actually feel like it's incredibly apt. But a definition of stress, way beyond anything relating to the IT industry, is having responsibility without having control. If you have a sense of responsibility, but you can't control the thing that you're responsible for, that's very stressful by definition. And what's happening with deep systems, if you imagine these black dots in this pyramid structure being services, if you are a service owner at that top dot, all you can really control is your own service. The whole point of moving to microservices is to have separate, independent control of different services. But the downside of that is that you really don't control the other services. However, when you send requests out to other services, if they go down, it's going to break your service too. So in a weird way, you are actually responsible for them, where if your dependencies are not working correctly, you are not working correctly. And that the relationship between what you can control being very small and what you're actually responsible for being, in many cases, quite large in these systems, is responsible for that leads to a great deal of stress with operators. And I think if we proceed, to the next slide, that you can think of it this way: as the system gets deeper, you as a service owner only control your own service. That is a constant. But the amount of system that you're responsible for grows quickly. I mean, it's the area of that triangle underneath you. It's growing faster than the depth itself. And the role of observability is to shrink the gap between what you control and what you're responsible for, both by giving you more control over the things underneath you, and in some ways reducing your responsibility for it. If you can find that there's an issue downstream, you should be able to hand off. People talk about mean time to resolution, MTTR. Some people on my team joke around about MTTI, mean time to innocence. It's this idea that you get paged and you want to figure out who's actually responsible for this issue and hand it off to them as quickly as possible, not just selfishly, but also because you want the person who's actually able to fix it to be triaging the issue. You don't want everyone running around in a disempowered way. So observability can help with that as well. And observability is really about shrinking that gap and thus reducing the stress of people responsible for these systems, both the operators and at some level the management.
I'm just thinking MTTGTMOOB, which is mean time to getting the monkey off your back.
Yeah, that's a better one. Yeah, I like that.
Which is really interesting. I mean, the whole situation here and it's kind of like many things in technology. It's defined by what it's trying to avoid. So observability is not necessarily a thing in itself. It's the solution to the problem of a lack of observability. And what you're saying, when you've got a lack of observability, you can't solve, you can't diagnose, you can't then ask someone else to fix something, etc. And similarly, this gap shrinkage, it's not necessarily about trying to make things more observable for their own sake. It's actually about reducing stress. It's about giving people the ability to work faster on the things they're working on because they're not distracted constantly by the things that they shouldn't be distracted by. So it's solving the complexity problems, but the complexity problems largely are almost people problems when we look at it that way. Would that be fair?
Absolutely, yeah.
Good. Well, that's good. And we've got this far. And the obvious point to make would be, well, we've got lots of data coming in from lots of systems at the moment. We've certainly got plenty to observe, but I think what we're going to find out in the next section, if I may, is why what we are currently able to observe isn't necessarily giving us observability. So why don't I hand over to you, Ben, in terms of the top three things that we might be observing right now and why that doesn't give us observability straight away.
Yeah, thank you. So there's this idea in the observability world that there are three pillars of observability, and they're typically referred to as logs, metrics, and distributed traces. And the story goes that in the olden days, Google and Facebook and Twitter and companies like that had an observability problem, that they developed logging, metrics, and tracing solutions, and then they solved their observability problem. And in some way, so should we. I can say, having worked at Google for a long time, that although they did have logging, metrics, and traces, they definitely absolutely did not solve their observability problem. Even if you ignore that piece of it, there are some significant issues with these three quote-unquote pillars on their own. I do think that all three of these data types is vital to the understanding of a system. And it's true that observability is better off having access to that data, but it's a pretty lousy way to structure a strategy around observability. And the easiest way to explain it is, I think, just to look at each one of these pillars on their own and to figure out where its fatal flaw is. I did a talk about this specific topic I think it's a 40-minute talk just about this one subject that was at KubeCon in 2018 called Three Pillars and Zero Answers. So if people want more detail, you can look that up. I'll do the 30-second version right now. Everyone knows what logs are. I think that's the one that's been with us since the dawn of time for computing. The trouble with logs in a microservices or deep systems environment is really pretty simple. It's that if you're going to use logs to understand and observe your system, you really need to log at least every time a transaction enters every service that it touches. And as you adopt microservices, the number of services is going up into the hundreds or thousands, and your number of transactions isn't going down. So you end up with hundreds or thousands times more logging data than you did before, but you're not actually processing that many more transactions, which is to say your business is not growing by hundreds or thousands along with it, and you just can't afford it. I think this ends up taking the form of top-down edicts to basically log less data because Splunk is getting too expensive or your Elk stack is getting too large or whatever. Logging does have a lot of advantages in that it's very simple and easy to understand and deploy, but the TCO really does not scale in deep systems because the amount of logging data is growing much faster than the value of that data. For metrics, which are just, this is started off with simple things like CPU and memory graphs, but these days also incorporates a lot of application level metrics like latency information about various endpoints, error rates, things like that. Metrics does address some of the TCO issues in that you're basically storing statistics instead of events. So it's not quite as painful, but if you're trying to understand why a system is failing by looking at a metric that has a spike, what you need to do is to basically group that metric by some tag. So for instance, if you're looking at latency for some kind of front-end service and there's a spike, you might want to group by the region or something, or ideally you might want to be able to group by something much larger like the customer ID. And the trouble with metrics is that you can't really group by things like customer ID because there are too many of them, and it ends up becoming, again, a significant kind of TCO cost issue. That is called cardinality. I don't want to go way deep on this, but if you look it up, this is the Achilles heel of metrics, is that cardinality.
I can imagine that you'd want to group by whatever made sense at that moment in time to solve the specific problem as well. So you'd want to flip groupings, like let's see how the customer view of this, let's see the experience view of this, let's see the transaction view of this, quickly,
exactly,
because you don't know which one's going to apply.
And since metrics are basically statistics, what you're doing is you're pre-aggregating all of your data. So in a logging world or in a tracing world, actually, it's possible to run more dynamic queries, but with metrics, you're basically saying in advance which statistical aggregations you want to do. And if you want to change your mind after the fact, you have to pre-aggregate all of these different possibilities. And that ends up being extremely expensive to the point of, again, not working. This will ultimately take the form of bills for metrics providers or broken infrastructure for metrics, but that's just the final back pressure. The issue is more fundamental about trying to use statistics alone to solve these problems. And then distributed tracing is the newest kid on the block of these three. I was responsible for some of the first production systems for tracing in the early 2000s, but it's really come to the fore in the last couple of years in industry in general. It does handle the cardinality issue and it handles the TCO issue, but it does it through some form of sampling. The amount of data is just as large, if not larger, as it was with logs, but tracing has some clever tricks around sampling, and that in turn also causes its own problems. Like I love tracing, I think it's important and it should be the backbone for observability, but it alone is not enough. You need to be able to join across to these other types of telemetry as well. And any observability solution that is just one of these pillars will not really be able to deliver a high ROI solution. And you certainly can't take one of each and paste them together. That's almost worse than the disease, I'd say. So this is observability and its fatal flaws as it's often marketed right now as these three pillars.
And as you say on the next slide, the ultimately it's like a garbage in, garbage out question for the data, isn't it? The telemetry data.
Yes, exactly. So observability, this is going back to the definition we were talking about earlier. Really, it's just saying if your system is this black box, observability in technology is how well can you understand what's happening in that black box without redeploying something. In an emergency, you really do not have time to debug your code, recompile, redeploy. You want to be able to understand things just by looking at the running system. And the only thing you can look at is the outputs, which are the telemetry, the metrics, logs, and traces. So you cannot have observability that's better than the telemetry. That's one of them. If there's one or two things you take from this whole webinar, it's that your observability cannot be better than your telemetry. If you have bad telemetry, you will have bad observability. If you have good telemetry, you still may have bad observability. There's still a problem to solve there, but the telemetry has to come first, and it has to be high quality.
And as we all know, one piece of data can change your view completely in terms of, was that correlation, was that causation? Oh no, it's this third thing over here that caused both of those things. So so it's hugely important to get the data right. So that's good. And at this point, normally in the presentation, we say, and Lightstep's got all the solutions. So that's really great, but we're not going to do that for a nice change. We're going to look at open telemetry as a principle. And what I'm going to do now, we've got another half hour to run on the presentation. We've got three segments, so we've got 10 minutes each. Is first, let's look at the open telemetry, and then we're going to be looking at how that delivers a better observability strategy, and then we're just going to run through an example. So hand over to you. And have you got control already? Yes, I believe you have. So
I do, yeah.
I'm gonna just sit and watch. Actually, you don't. Okay, well, you talk, and I'll click, and we'll work out that.
Okay, cool. Yeah. So this is a section around OpenTelemetry. The goal for OpenTelemetry is really to address the problem I was just speaking about, that there's no way to have high quality observability without having high quality telemetry. And 10 years ago, what you were doing if you wanted to solve this problem was basically to buy an APM product, which is probably kind of expensive. And a big part of the value proposition there was that you were buying a quote unquote agent, which you would plug into your application, and the agent would magically extract runtime information and infrastructure information and get it back into the APM solution. That was telemetry. That's what you're collecting. I think the issue with that, well, it's manifold, but among other things, from a customer perspective, you're literally locking yourself into a vendor. There's often a lot of overhead there, and it didn't really come built in. Like, it's not like open source software, which now runs most of the application stack. It didn't come built in with support for these particular vendors, and so there's just too much of it out there. I think no one vendor can really afford to cover the entire cloud native landscape in its 8 or 9 languages and thousands of different frameworks. It's just insurmountable. And so the idea with OpenTelemetry is to basically build an exchange where you as a customer can adopt OpenTelemetry and get high quality, portable, high performance telemetry out of your system and use it with any open source project or vendor that sees fit to consume that telemetry data. So I guess we can go to the next slide.
And a question here for me is, as we go along, how does this relate to how does this relate to the question that you raised just a minute ago, which is around the weaknesses of the existing pillars?
So that's a good question. I think the pillars themselves are valuable data sources. I think of them as pipes and not pillars. And OpenTelemetry, for me, observability is really about two totally distinct steps. Step one is to get high quality telemetry, which does involve tracing metrics and logs. Step two is to build some kind of strategy and solution that can provide a set of unified workflows that take advantage of that telemetry. And OpenTelemetry as a project is very focused on solving the first piece of this, of just gathering the data. And you can think of tracing metrics and logs as being kind of verticals of telemetry. OpenTelemetry is a very broad project that's, that has committers. It's a very robust, healthy project. It's part of the CNCF as well, and it has committers from 8 or 9 different vendors, a number of end user companies, a bunch of folks who just like writing open source software. And it's kind of a matrix. You have these different pillars, and then, well, I shouldn't say the word pillars. You have different telemetry verticals, tracing metrics and logs, and then these the project itself has something to say about instrumentation APIs, auto instrumentation, which is kind of like an agent where you drop the thing in, implementations that are vendor neutral, data infrastructure that you can deploy into Kubernetes, et cetera, data formats. All these things are part of the OpenTelemetry project, and it's all decoupled, which is something I really like about it. You don't have to adopt all of this to adopt part of it. You can kind of pick and choose. Like you could be running, Java Spring, and you just want automatic instrumentation. That's it. Great, OpenTelemetry can do that. You could be a Kubernetes platform team, and you want to be able to deploy a sidecar that collects all this data. You can do that. But you don't have to couple these things. It's a very broad but decoupled project that just focuses on this common need of getting high quality telemetry without any kind of vendor lock-in. If you want to get involved, you can also go into the project and look at the number of special interest groups within OpenTelemetry. There are probably several dozen of them at this point. And each one of them basically handles a single box in this matrix. But it's a pretty cool project. There's a lot of stuff going on.
You just did
maybe
that.
I should stop trying to control. I just hit the.
Yeah. No, that's fine. I'll keep control on the thing. Some
technical difficulties. My apologies.
That's all right. Our audience loves it. Right, so we're back on this slide. There you go.
So I was just going to walk. I'll briefly walk through a couple of sections of this. You've got basic instrumentation APIs. So this is if you're in the application layer and you want to add some kind of business logic to the telemetry. For instance, if you want to add a customer ID or something like that, you can do that in a portable way. If we go to the next slide, automatic instrumentation is the value prop is very simple. If you're running a Python app, all you need to do is to wrap your Python app in an OpenTelemetry agent, essentially, and it will automatically install all the appropriate instrumentation and get that data out of your application for you, and you don't need to change any code or redeploy or recompile anything. And we have those in many different languages. The next is this idea of canonical implementations. If you are, this probably is less relevant to this audience, but if you're interested in building open source tooling for telemetry or observability, it was a very difficult thing to get all this data previously. And with OpenTelemetry, you only have to write a couple of lines of code to write a consumer for this fire hose of telemetry data, which makes it much easier to build special purpose tooling. And some end users are building, some end users are building some really sophisticated things that are particular to their business or their application using these interfaces. The next data infrastructure, I was referring to this earlier, there's an open telemetry collector, which can either run as a sidecar in Kubernetes or as its own separately managed service. And there's an operator that makes it very easy to deploy it. This is something that people use in order to have standardized, obviously data collection. The telemetry has to go somewhere, and the collector is one of many ways to basically shunt that data from one place to another. And then finally, these interoperation formats. A number of these are having to do with the actual bits and bytes that we use to represent traces and metrics, things like that. There's also a W3C standard that's evolved around tracing and context propagation, which is closely related to the OpenTelemetry project. All of these things make it easier, again, to build application software and tooling that interoperates with common standards. And OpenTelemetry is trying its best to reduce the number of those in the outside world to one. That's our goal, to get it so that there's only one way to represent these different data types, which of course just makes everything a lot easier. It's always a challenge in an open source environment to accomplish that, but I think we are at least making things better rather than worse. But those interop formats are also part of the OpenTelemetry project.
Is the open source community a deep system? That's the question. Has OpenTelemetry, where is it on the journey to solving solving the traditional telemetry issues, would you say? I mean, is it 80% there?
So that's a great question. OpenTelemetry, the project, is an unusual open source project. There were two projects. One was called Open Tracing, which, as by its name, was was very similar to OpenTelemetry, but was focused on tracing specifically, which is part of the CNCF. And another project called Open Census that was initially developed at Google and open sourced, which was similar to Open Tracing, had a little bit more scope, but also had some differences. Those two projects were realizing that the world really wanted them to converge into a single project. So OpenTelemetry is really the next major version of both Open Tracing and Open Census, and provides backwards compatibility for both. So in a sense, if you adopt Open Tracing or Open Census, you have a clean migration path into OpenTelemetry, and then people are now adopting OpenTelemetry on its own. I'm not sure if I have permission to say which companies are, but there are a number of very legitimate enterprises that are using OpenTelemetry components in production already, and we see that folks who are considering Open Tracing or Open Census are now moving into OpenTelemetry instead, because it is, just as of a few weeks ago, is now officially in a kind of beta deployment where it's suitable for use in real production applications. It was about a year and a half of work to get it to that point, but we're pretty excited about where it's at. You can understand the maturity of OpenTelemetry for any particular aspect by going to the GitHub repos and poking around or looking at the website. It does depend on what it is you're trying to do, but if you're trying to do the vanilla stuff, like if you're using Java or Python or C# or whatever, and you want to just get basic telemetry out of your application, that part I would say is now pretty mature. There are pieces of it that are much more exploratory, and they're labeled as such. The project is not meant to have a single maturity. It really depends on what you're trying to do with it. But the main aspects of it that I think enterprises actually rely on, I would say, are open for business at this point.
Cool. I mean, that's great stuff. And without mentioning the names of any organizations, we can use them as we move into the kind of on the downhill slope of the webinar, which is to talk about how to apply some of this stuff. Oh, there's a build. So I'm going to just stick these on the screen, and then let's talk it through. Oh, sorry. Let's go back to that one. That's a taste of what's to come. So what does doing it properly mean? And we've got 16 minutes, so let's get some theory, and then we'll work through this lovely graphical example, and then a few demo screenshots.
Sure, yeah, theory is boring, so I'll be concise. So really, we've been talking about what observability is not. We've been saying that logs, metrics, and traces are just telemetry, and I think that's absolutely true and it's very important. But what is observability? It really, like anything, it only makes sense if you think about it in terms of use cases. The three use cases that make sense to me, really, the only reason that any of us in this industry have jobs is to innovate quickly. And that means being able to deploy software with high confidence and frequently. So confident releases are something that observability can help with. When things do go wrong, which is inevitable, it's not an if, you need to reduce the time to resolution. Observability is extremely helpful in that environment. And then finally, just for improving the steady state, if you have a quarterly goal to improve performance by 20% or what have you, observability, like any kind of optimization, you have to profile first, and observability is an invaluable profiling tool. And then as a meta point, I think the telemetry and the data should always belong to the customer. Lightstep has always made that a priority. I personally started the open tracing and open telemetry projects along with a number of other folks that had similar goals, and that's partly because I really do not think vendors should control the data. Vendors should be providing value through functionality, not lock in through data. So I would encourage people to pursue that path in the observability strategy as well. So if you want to switch vendors, it's not an impossible task.
And there's increasingly a security and privacy question. It's really interesting to see how a lot of enterprises these days don't want their code to be within a cloud provider's jurisdiction. So quite happy for the binaries to shift, and but not the base materials, because it could be revealing of what they're up to, and the same could be said for telemetry data. It would be my thinking.
Absolutely, yeah.
So I'm still in control. So you need to tell me when to shift on these slide transitions. So
Cool.
use the word
well, let's just build the slide out. So
okay.
The conventional wisdom, again, is that you have metrics and logs, and maybe if you're lucky, traces. This is what they look like. I've torn this down a couple of times in this webinar, so I won't do it again. But I will just say, if you have to debug things by having 3 tabs open, you're doing it wrong. We can kind of leave it at that and move to the next slide.
Okay.
You don't want to be doing that. So really, there's 2 really big pipes of data, which are metrics and logs, and this is just data. And if we advance, the trouble is there's too much of it. Again, going back to the stress of deep systems, if you're at the top of that triangle, you have to understand all of the metrics and logs below you, not just from your service, but everything underneath you, in order to properly execute responsibility for your service. So if we go to the next slide, the challenge, if you kind of build this out, is if you use tracing data, what the tracing data can really do is provide context. So in this diagram, what we've seen is that you have a hotspot underneath you. What tracing can do is say, okay, well, there are only 3 services on the critical path to that hotspot. Everything else in your system, and in this diagram, of course, I only have 6 or 7 of these little dots. In reality, it's more like hundreds. What tracing can do is rule out everything that's not on the critical path. That is an enormous improvement in terms of what you're responsible for. And
so give me a scenario here. Give me a day in the life kind of situation where the context really shines.
I'll give an example of that in a minute, but just to preview it, let's say that you depend on Kafka, and there's some topic that's running really hot, and so there's too much stuff in that topic. Kafka as a whole can then lock up, and everyone using Kafka will feel that back pressure, and your entire application can kind of grind to a halt. This happens very frequently in Kafka deployments in production. And understanding where that traffic is coming from is an extremely difficult problem, because it's often, it's not just the immediate peer, but you have to go like way down, way up the stack to figure out where that is. Tracing data will be able to answer that question for you, and thus informs the investigation. The trouble is, if something like Kafka or a SQL database or some other infrastructure service goes under, everything breaks. So it's not like you have a little thing that's broken, everything is broken. So you see fire everywhere, but you don't know where it actually started. Tracing is extremely effective at figuring out where the initial problem actually came from, and thus eliminates most of the fire from your consideration and focuses your investigation on the piece that's actually relevant. I'll give an example of that later with screenshots and so on.
Okay, and that reminds, I mean, observability is one thing, we're using all these terms, but back in my network management days, knowing which way to look it's not just about being able to observe, it's knowing which way to face when you're doing it. So the problem's over there, it's in the database, or it's in the servers, or it's in the network, or whatever. Just being able to kind of start restricting your search, and that's what traces start to provide, which direction to head in to solve the problem.
Exactly, yeah. So if we go to the next slide, I believe, if we started with this, the tracing can reduce, one more build here, will reduce the search space in metrics and logs to just the metrics and logs that are relevant to your investigation. I think if there's one thing I would say that I believe will ring true for everyone who's actually tried to debug in a deep system environment is that it's not, when things go wrong, it's not that you don't know it. Like, you're very well aware that things are going wrong. And if you open up your dashboards, you'll see it everywhere. The problem is that you don't know which of the badly broken graphs is the one to look into next. Tracing, if properly integrated into unified observability, can provide that context. It's a very difficult thing for an observability vendor to deliver. I guess at some level this is, I should keep my Lightstep hat on. I mean, what Lightstep has done is to take that tracing data, which is extremely high throughput, and to milk it for everything it's worth, not just as traces, but actually as context that informs the rest of the investigation. And by doing that, we can deliver some pretty, I think, unusual and impressive results, which we'll get into in the screenshots in a minute.
Awesome. So before we do that, we've got another poll. So let's launch that. And as we're launching it, I'll start asking the question, which is to you, the audience. Where do you see unified observability being most useful? So you're there, you're the firefighters, you're diagnosing and resolving issues. Do you see it as that MTTR being the real key criterion on time to resolution? See it as an overall operational cost question, or as Ben suggests, is it about improving speed of innovation and being able to ramp up how quickly you can deliver new releases? More generally, are you just seeing it as something that can improve overall performance and reliability, or I know collaboration's a big topic among the whole dev and ops, and getting all the different collaborators and stakeholders working together. So maybe that's the driving force for unified observability. So let us know what you think, and while we're doing that, why do people come to you, Ben? So not a direct sales question, but what problem do people want you to solve for them?
Yeah, I mean, I think what we often see is that people are having difficulty getting end-to-end observability of their own systems. Like, individual service owners know when their own service is non-functional, but they don't know why. There's often a lot of finger pointing within organizations during incidents because no one can figure out who's responsible. There are often significant brand damaging, latency and performance reliability issues that are affecting end users. There are often difficulties understanding where the cost is coming from within infrastructure. All these sorts of things are, and of course, just the speed of deployment is being inhibited by a lack of confidence. People are only deploying Monday through Thursday and don't deploy on Friday at all because it's too frightening to imagine a bad deploy turning into a weekend firefighting drill. Like, it's a pretty profound level of paralysis in some organizations due to a lack of observability. And people turn to Lightstep to address those issues.
Oh, and there we go. So yeah, and I think interestingly the time to resolution question is fascinating because it is more likely to be organizations that are facing the pain. So some of those questions are more broadly kind of preemptive and proactive and future facing. whereas time to resolution is very, we've got a problem here, we need to solve it. So that maps onto what you were saying there.
Mhm.
So okay, so let's jump back into the deck then, so we've just to wrap up. Then we've just got a few slides to make this real. So there's a screen with things going on.
Yeah, I just wanted to provide, this is not demo data, this is actually Lightstep's internal systems. Maggie is the metrics aggregator that we have inside Lightstep, and I wanted to just walk through an example.
Nice.
So I've circled an incident we had, nothing massive, but definitely you can see something bad happened. That little vertical line with the circle at the top is a deployment. So after deployment, there was a regression. What you'd want normally in a metric system, you'd say, I wonder what that is. And you'd start opening up other graphs and trying to figure it out. What we really want to do is just click on it. So if you go to the next slide, if you click on that thing, Lightstep says, would you like to investigate this regression? Which is, oh, yes, I would. So I'll click on the arrow, and Lightstep will say, okay, well, you can go to the next slide. Let's compare it to a baseline period. And you can choose whatever baseline you want. It's recommended one here. That's more business as usual. And then after hitting the compare button, go to the next slide, we start seeing some interesting things. So before I actually show the UI, what's interesting here is that Lightstep has assembled, roughly 1,000 transaction traces, full end-to-end transaction traces from those two narrow bands, the baseline and the regression. And we've done a very complex kind of ML-based statistical analysis of both of these in order to understand what's actually going on and what's different between the regression and the baseline. I don't believe there's anything else out there that can do even the collection, much less that analysis. And what you see if you advance is some pretty impressive stuff. So what we do here is yellow everywhere is the regression and blue everywhere is the baseline. And we do everything, these histograms in the top left show you that indeed you can see that things are slower in the yellow histogram than in the blue baseline. And the question is, okay, well, why? Like, what's slower about the yellow histogram? And we've automatically extracted statistical features of these two data sets that differ the most. If we go to the next slide, the first thing we show you is that most of the latency is actually on this thing called Sarama Sync Producer send messages, which is basically a Golang Kafka client, which tells us the reason that this new thing is slower than the old thing is that Kafka got slow. This goes back to the idea of Kafka, Kafka is a separate service. It's actually several layers below us, and we've immediately, the first thing we show you is that the reason there's a difference between the baseline and the regression is Kafka. Of course, you might say, well, why? Like, what about Kafka? So if you go to the next slide, it's figured out that there's a specific topic in Kafka, public late weight aggregate, which is 250 milliseconds slower in the regression than the baseline. That one topic is responsible for this regression in this Maggie service. And we've done that without ever looking at a trace or really looking at anything other than just clicking on the most obvious possible thing. Click on the regression, say compare, and the first thing we show you is Kafka, and it's actually the specific topic in Kafka that's hot right now. And you can see the overlaid latency contribution, the highlighted orange area. This is the representation of latency just for that one Kafka topic. I could go on and on. We only have not very much time, so I'll kind of stop at this point. I think there's one more slide that just shows you. You can look at example traces to be more concrete to see exactly how one of these transactions actually plays out, including all the logging data. But this shows you how metrics, logs, and traces can come together into a unified experience that actually helps you diagnose things. If you want to try this stuff yourself, there's a self-serve demo that doesn't involve talking to anybody that is really pretty compelling. If you go to lightstep.com and just, there's a try it yourself kind of button on the front page, that brings you into a sandbox where you can play through a bunch of examples like this and see what it does. But it's much different if you can take all this telemetry data and actually use it to address these operational questions that you started with.
Awesome, and that takes us really nicely to the final slide. And I'm going to ask you one last question, if I may, which is, if you were to advise anybody that was kind of really struggling right now and looking to solve the MTTR problem and just seeing the world as a pool of spaghetti and too much data and not enough insight, what would you do? what would you say to them as the first thing to start with?
I'd strongly suggest checking out Lightstep's Play demo at the bottom. I think if nothing else, it will show you what's possible. And then in terms of gathering the data, I think you can't go wrong with OpenTelemetry. Whether you want to use Lightstep or open source or one of our competitors, it's the best place to start for actually gathering the data. So those, to my mind, are the two first things I would suggest.
Okay, well, awesome. Thank you so much, Ben, for joining me on this webinar. I learned a lot, and I hope our audience did as well. And you guys out there, thanks for joining, and you know where to find us in the usual social channels. If you've got any questions or feedback, let us know. But it remains for me to say once again, Ben, thank you very, very much for joining us on this webinar, and do tune in next time.
My pleasure. Thanks so much.